So here in lecture 11.6, we're going to continue our exploration of maze routing, and now we're going to start looking at implementation mechanics. So this is the first of 3 lectures in a sequence on implementation mechanics. What we've talked about so far are features. How do you do 2-point nets? How do you do multiple point nets? How do you deal with multiple routing layers? What interesting things can you do if you put cost values in the chip surface? So these are all of the what you can do with the maze routing method, but we haven't actually seen something like pseudocode yet. And I keep showing you things where magically the cost values appear in the grid. All of the 2s appear in the grid, and then all of the 3s appear in the grid, and then all of the 4s appear in the grid. That's not an algorithm. That's magic, right? We need to actually show mechanically how do those things actually happen. There's some very interesting terminology, there's some very interesting mechanics, there's some very surprisingly nice, not very complicated pseudocode that's the core of all real maze routers. So in this, the first of our 3 implementation mechanics lectures, let's just start looking at just, algorithmically, how does this maze routing stuff really work?
So here in the first of our implementation mechanics lectures, we're going to start talking about how you really build one of these maze routers. We've got 2 kinds of questions. The first is representation, data structures. How do you store the routing grid? What do you need in each cell? And perhaps most importantly, and what's really going to drive this design, how do you represent the state of the advancing path search process? Turns out, not really with the routing grid. Perhaps that's a surprise. And then on the algorithm side, let's just think for a minute. If you can really only process one cell at a time, then which cell is the next one you label in the search process? And does the order matter? And how do you do that rapidly? So let's note that when I was doing the animations on the previous sets of slides, I would just have all of the cells that cost 5 appear at the same time, and all of the cells that cost 6 appear at the same time. And clearly, if you're writing a sequential computer program, that's not really going to happen. You're going to have to do something a little more clever than that. How? What's the data structure that lets you do that? How do you do that rapidly? Let's go talk about that. So here's a big goal, and actually this is an overriding goal for maze routers, is efficient storage. A big layout needs a really big grid, and so one of the consequences of that is that we're going to put as little as possible in each cell. And an interesting side effect of that is that we are not going to store the path costs in the grid cells. If you need, like a double floating point number or something like that, that's actually a lot of bits. That's way more bits than it turns out I really need in the cell. I can get away with having the grid cell be a really pretty small object, maybe 16 bits, maybe less depending on whether I play some tricks. The reason for that is that it turns out that I don't need to store and track and manage the process of the search expansion of the wavefront using the grid. And here's a sort of an interesting insight. I'm going to draw a picture of this on the next slide. Only the cells that are most recently labeled during the search are useful for expanding the search. So this is an important term. There's a name for these cells. The cells at the edges of the search region. It's called the search wavefront. And it's really the wavefront where all the action is. It's the wavefront that's really the most important. So here's a wavefront. I've got my 3x3 routing grid here. The source is kind of in the middle. The target is in the bottom right. And I've got things labeled. So there's a source cell. There's a diamond of 2s around the source, a diamond of 3s, and a diamond of 4s. And the 4s are all highlighted. They're in red, and they're big yellow boxes around each one. The wavefront is the frontier of the active search region. It's the neighbors of these cells that are really worth looking at to try to extend the evolving path search. And I'm going to emphasize that by actually drawing little stars on all of the interesting neighbors. Oh, look, I put a star on the target. That's happy. So I'm going to put a star every place. I'm just going to say it again. The frontier is where all the action is. The frontier is the edges of the volume of the routing grid that we've searched, and we know the path cost to get there. And in order for the search to continue, I'm going to label the cells that are unlabeled as yet, the neighbors, the adjacent neighbors of these frontier cells, with a new path cost. And so the only cells you need to look at in this process are the edges of the search region, the wavefront. So the implication is I'm not going to store the path cost numbers in the grid. I don't need to. I'm just going to store these highlighted wavefront cells. I'm just going to store where everything interesting is happening, the edges of the search volume itself. Turns out I'm going to need a special data structure to do that. Now, I've got another routing grid here. It's also 6 by 6. The source is in the upper left, the target is in the lower right, and there's a little region of high-cost cells now, a region of 3s to the east and south of the source cell. Every other cell in this grid costs 1. And if we just start expanding things in minimum path cost order, you can sort of get a sense of what's going on here. So we expand the source cell, which costs 1, and we reach the neighbors. 3 of the neighbors cost 2, one of them costs 3, and so that one gets labeled with a 4. So the second thing we do is we expand all of the cells that cost 2, and we see what happens. And the answer is we get a whole bunch of cells that cost 3. No surprise, we get a partial diamond there, but we also get a particular cell that costs 5. I'm circling it because that's the cheapest way to get to that cell. We expanded the 2, we added a cell that cost 3, we got a 5. If we go forward, what we should do is we should expand all the cells that cost 3 and see what happens. Well, this is what happens in the next slide. We see a bunch of cells in a diamond-like arrangement that cost 4, but the diamond is sort of retarded, if you will. It's kind of pushed in because that region of high-cost cells that cost 3 is sort of pushing back and saying, wow, it's really expensive to go here. And so we don't expand into that region. We're not going to get into that region until we expand a little further some of the other cells. So even with non-uniform costs, this all works. So the wavefront is the set of cells that have already been reached in the expansion process that have neighbors that we have not reached. So again, I'm going to draw little stars. Little stars for the neighbors that we have not reached. Again, I hit the target, that's happy. Little stars. The wavefront are the cells we've reached and labeled with a path cost. Their neighbors are the cells we have not reached. We index the wavefront cells by their path cost. So in this particular example, there are some 4s in the wavefront, and there are some 5s in the wavefront. They don't all cost the same thing. So unlike the very first versions of this algorithm where we expanded all the 3s and then we expanded all the 4s, the stuff in the wavefront could have different costs depending on the scenario of high cost cells it sees in the grid. We're going to expand these cells to grow the search wavefront in path cost order, cheapest cells before more expensive cells. This is famous. This is a famous algorithm. This is Dijkstra's algorithm. Originally invented, wow, way back in the 1950s for shortest path search through a graph with weights on the edges. It works perfectly fine for gridded maze routing. If you want to think of the grid as a graph, think of the center of every cell as a node in the graph, and there are edges to the north, the south, the east, and the west neighbors. We assume the wavefront is an indexed list of cells already visited during the search, and we label them with their path cost. The path cost is the cost of all the cells on this partial path to the target, just the sum of all those cell costs. How does the wavefront grow? This is the essence of the maze routing business. This is the expansion process. Here's a word version. We're going to kind of walk through this with some pictures and such, and then we're going to do pseudocode at the end of this lecture. You find a cheapest cell from the wavefront, and then you find its neighbors. And so let's call those neighbors N1, N through to NK of the cell that you have not reached yet. And then you compute the cost of expanding the path to reach those new cells. You add these new cells back into the wavefront data structure because they are now the edge of the wavefront. And you index them by their computed path cost. So if N1, N2 to NK are these new cells you just reached, the path cost of N1, the path cost of N2, and so on are the indexes you use to put these things in the wavefront data structure. You also add to each of these cells a pointer to how you got this cell, which is to say a pointer to C. That has a special name. It's called a predecessor. We're going to talk a lot about predecessors. That's how you do backtrace to find the path. You also mark the routing grid to remember that you reach these cells. You don't have to reach them again. Okay? This is in part how you tell, as the wavefront grows, what are the things that are new that are unreached that you can get to. The answer is you haven't marked the bit in the cell that says reached yet. When you're done all of this work from cell C that you removed from the wavefront, reached its neighbors, computed all this good stuff, you remove cell C from the wavefront. It sort of dies. And then you repeat with the next cheapest cell on the wavefront. So I need some precise terminology at this point because otherwise we're going to get confused. And the good news is that there are some simple terms that have very clear meanings. So the path cost is the sum of all the cell costs on the partial path from the source to a cell. It's what we use to index the wavefront. The wavefront is the frontier of cells for which we have computed the minimum cost path. Reached means a cell is reached when we compute the minimum path cost for it and we put it on the wavefront. A cell is expanded when we remove it from the wavefront and use it to reach its unreached neighbors. There's a very nice kind of crisp terminology here. When you reach a cell, you compute what it costs to get there, and you put it on this special data structure that tracks everything by its cost. When you remove it from this special data structure, you expand it. What do you do with it? You use it to reach some new stuff you haven't reached yet. When you've expanded it, you can throw it away. You don't need it anymore. Okay? The whole point of the wavefront is that it's the edges of that big search volume that are exciting. So, things enter the wavefront when you reach them. Things leave the wavefront when you expand them and use them to reach new things. This whole idea is Dijkstra's approach. Expand cells in their minimum path cost order. I've got a nice picture here on the next slide. So I've got a great big yellow box, which is the routing area. It's got a source and a target in it. There's a big blue diamond. It's already expanded. I won't revisit those cells. The source is in the middle there. There is the current wavefront, which are the red cells on the edge, little red boxes. I've got a sort of a blow-up of one of those red boxes and its neighborhood, the 9 cells of the neighborhood, including the source cell. The yellow stuff are the cells we've just not reached yet. And so I've got to zoom in on the little pointy end of the wavefront there. There's a red cell in the center, that's on the wavefront. There's 2 other red cells that are the other part of the wavefront. A blue cell, which is some stuff we've already expanded, and some yellow cells that we've not reached yet. Let's just sort of talk our way through this. We're expanding the center cell, so that's why I put a star on it. We're expanding it means we have removed it from the wavefront and we're using it to reach its neighbors. What neighbors are we reaching? These 3 neighbors. We are reaching its north neighbor, its east neighbor, and its south neighbor. Are we reaching its west neighbor? No, we are not. Put a big X over there. Why not? We've expanded that cell. We've already reached it. We got there already. We don't need to get there again. And so I'll just click on that and say, this cell's been removed from the wavefront. It's already expanded, which means it's been reached. We mark the grid. No, you don't get to look there again. Okay? And let's just assume that the other cells, the 2 other red cells, have not been expanded yet. They're sort of sitting in the wavefront. So it's a nice, crisp language. You reach a cell, you figure out what it costs to get there. You put it on the wavefront. When you figured out all the stuff you can reach from one of these cells, the cell with a star on it, it is expanded. The process of reaching your neighbors is expansion. When you're done expanding a cell, you can get rid of it. You don't need it anymore. Thus, we don't need to put all the costs in the grid because we don't need to know all of the stuff in the past. We just need to know all of the stuff in the present and the future, which is the edge, the frontier of the wavefront. Some more terminology for you. The predecessor of cell C on the wavefront, we write that as pred C. It's a tag that tells the direction from which cell C was reached. And you want to think of that as, how did we find C? We mark the cell C data structure when we add it to the wavefront, and we mark the grid itself when we reach that cell. Why do we have to remember this? Because we're not marking numbers in the grid anymore. And so to backtrace the path, I can't just follow the numbers in decreasing order anymore. I need a real trail that points cell to cell back from how the path was put together. So let's just be very clear about how the predecessor stuff works. So let's assume I have 2 routing layers. Then the conventional way of sort of denoting this stuff is that there are 6 predecessor tags. North, south, east, and west, that's the direction from which you were reached. And then let's assume there's 2 routing layers. So for 2 routing layers, there's up and down. You know, either I went from layer 1 to layer 2 or I went from layer 2 to layer 1. And so in all these pictures, the red cell is being expanded and the yellow cell is being reached. Cell B is being expanded, cell C is being reached. So here's a little picture. Cell B is being expanded and it's reaching cell C. Okay, so you look at cell C in this picture, so B's on the top and C's on the bottom, and you say, cell B, how did I find you? And the answer is from the north. Right? B is north, from the north. So you mark C and say north. That's the predecessor. If you flip this scenario and B is on the bottom and C is on the top, you say, hey, cell C, How were you reached? And the answer is from the south. B is to the south. Right, so you mark cell C with its predecessor and say you're south. Now we've got B on the left and C on the right. You say, hey, cell C, how were you found? And the answer is from the west. So you mark its predecessor as west. You flip it, cell C is on the left and B is on the right. Say, hey, cell C, how were you reached? Answer, from the east. B is from the east, and so you mark the predecessor as east. Now, one of the reasons why we use these tags is I don't need a lot of bits to specify these tags. North, south, east, west, up, down, 3 bits. Okay? So I don't need to put a double, 64 bits in every cell in the grid. So far, it looks like I need 3 bits for the tag, maybe 1 bit to know that I've reached it, and maybe a little bit of, a small number for the cost. So I can do it with a very small number of bits. So just to emphasize, the predecessor is the direction from which cell C was reached. Now again, let's look at the fact that we have 2 routing layers, and let's look at the up-down tags. So cell B is on the bottom, and I reach up. Okay, I expand it up, and I reach cell C on layer 2. When I say, hey, cell C, how were you reached? The answer is from below, down. I label it with a predecessor, which is down. Now C's on the bottom, B's on the top. Say, hey, cell C, how did I reach you? From above, from layer 2. So what do I give you as the predecessor? Hey, predecessor. Hey, C, what's your predecessor? Answer, up. I was reached from above. The predecessor is still the direction from which the cell was reached. Now, why are we marking the predecessor? Because I can't do this anymore. This is an old example, the 6x6 layer 1, layer 2 example, source in layer 1 at the upper left, target in layer 2 at the bottom right, 2 vias in the middle of the grid and the right of the grid, a vertical band of blockage on the layer 1, a horizontal band of blockage on layer 2. This is the expansion that we did. And here's the nice animation of what I can't do anymore. I can't find this path by saying I reached the target with an 8, so go look at the cell for a 7, go look in the cell with a 6, go look in the cell with a 5, go look in the cell with a 4. Oh, the 4 is in the other layer. Okay, go look at the cell for a 3, go look at the cell for a 2, go look at the cell for 1. I can't do that anymore. I'm not putting these costs in the grid. I didn't need to put these costs in the grid. It's actually much too expensive to put these costs in the grid. All right. This grid does not exist as something that I put the path cost in. So I need to do something different. And so that cool different thing is that whenever I reach a cell, I mark the predecessor in the grid. Okay? So as a consequence, backtrace is easy. I follow the predecessor marks in the grid. Right? So this is exactly the same process, right? I reached the target T on layer 2 on the right, and I say, where do I go? I was reached from the west, so I go to the west. I go to the next cell, how was I reached? I go to the west. I go to the next cell, how was I reached? I go to the north. I go to the next cell, how was I reached? Down. Oh, okay, I go over to layer 1. How was I reached? West. How was I reached? North. How was I reached? North. How was I reached? Oh, it's the source. Right? So this is a very simple, beautiful idea. Instead of putting the numbers and sort of following them, and let's be honest, the numbers get a little tedious when you have to start calculating costs of cells that are not 1. Instead, we just put this little mark in that says, how did I get here? And it's like a pointer in a computer program. There's only a couple of places I can point to. North, south, east, west, and some layer stuff up and down, or maybe a few more bits if I have a few more layers. So we just embed these little bit things in the grid cells to say, where do I go? Works great. Now, let's talk about the detailed mechanics of expanding and reaching. So recall, I expand a cell when I pull it out of the wavefront and I use it to reach its neighbors. So I am expanding cell B, which is in pink on the left, okay? And the predecessor of cell B is north. And the path cost of B is 12. Let's just assume we know all those things. And I'm seeing unreached neighbor C to the east. And so I compute the cost to reach C as 12 plus 3 because C's cost is 3. So it's 12 plus 3. And I add this new cell object to the wavefront. Okay, the layer is whatever the layer is. Let's assume that's 1 layer. right? The cell location is C, so that's either some coordinates or a pointer back to where this thing is in the grid. The path cost is 15, and the predecessor is west because I reached this thing from B, and B is to the west. And now I'm going to mark cell C as reached, okay? I'm going to mark that bit in the grid as true. I won't try to put it on the wavefront again. I won't try to reach it again, right? So you expand a cell when you pull it out of the wavefront, you reach the other cell. You compute what the path cost is. Path cost from B plus path cost of C. You compute the predecessor. I got you from the west. You mark in the grid, hey, I don't need to reach C again. That's it. It's not bad. Not a lot of work in the inner loop. And I'm just showing here the little illustration that says, remember you have to mark in the grid that it was reached because I won't try to reach this cell again. So here we are finally. I've got pseudocode. Okay? So I've got sort of the, the start, right, up at here, which says the wavefront is the source cell. Let's label the source cell. And then there's the big while loop that says while we have not reached the target cell, keep searching. And then there's the how you quit. Okay, well there's one way you can quit, which is if the wavefront is empty, you quit, you failed, right? And so I'm just going to write fail. If the wavefront's empty, there's no path. Otherwise, you get the lowest cost cell on the wavefront data structure, and if it's the target, then you do the backtrace and the cleanup, and so this is the little part that is success, right? And the rest of this is actually the real expansion process. For each unreached neighbor n of C, mark n in the grid as reached. Compute the cost to reach it. You know, the path cost of that cell n is the path cost of C plus the cell cost of n. Mark n in the grid with the predecessor direction so you know how to get back there. Add the cell n to the wavefront indexed by its path cost because the wavefront just grew a little and these are the new cells. Delete C, you've used it, right? So you reach a cell, it enters the wavefront with the right computations. When you've used a cell to reach its neighbors, you've expanded it, you get rid of it. So you only store the wavefront, which means it's smaller than all the stuff in the grid. The core algorithm is surprisingly simple. One of the things that's true is you can build a lot of router with not a lot of code. I will mention, for example, that the kind of the reference router for the final program is something like 500 lines of code. Not a huge amount of code, even with all the features. Vias and bends and multiple layers and all this good stuff. It extends naturally to all the features that we talked about in the sort of the lecture up to here. You can do multi-point nets. You just mark all the cells of intermediate paths as source. Okay, and you push them all in the wavefront and you run. You can do two routing layers. You just use parallel grids, and when you expand to reach the neighbors, make sure you check up and down and use the right predecessor stuff. So the multi-point stuff and the two-layer stuff and non-uniform cost, we already put that in the pseudocode. Right, you just mark the cost in the grid. For vias, whenever you reach a neighbor on a different layer, you just add the via cost. So it's just part of the path cost. Right, so it all just works. It's actually quite elegant. What's missing? Real data structures. I've still been sort of talking around the point. I need a real data structure. Let's go do that next.